So let's start by looking at our electron configuration for carbon. And so we've been looking at this, for a few years now, so we can piece this together. We know it's 1s2, 2s2, 2p2. Right? I like the symmetry of carbon with those two electrons in each one. And this is one way we can write out the electron configuration, but we know that there's other ways we can represent this. So you might have seen, box diagrams to represent this, where we have each of our orbitals that's represented with a nice little box. And this helps remind us how many electrons can go in each one. And we can use these spin arrows to describe our electrons. And we know that these three different 2p orbitals are the x, y, and z orientations. It doesn't really matter what I label as x, y, and z. And so I've done a few things here, right? We can see that I paired them up from the lowest energy orbital up, and I put electrons in those lowest energy orbitals before I put electrons in higher energy orbitals. And so this is good old Pauli exclusion principle that you have been seeing again since Gen Chem. The other thing to note is that when I got over to my 2p orbitals, I put my electrons in different orbitals. This is Hund's rule, and I made sure that their spin state was or they had the same spin state. And we're going to get back to this in just a few minutes. But what kind of data can I use? This doesn't tell me about which was my low or high energy orbital. These are just ways of describing this spin state. So what kind of data do we have that allows us to describe the actual energy of these orbitals, which will be very important? One thing we can use is actually something called photoelectron spectroscopy. And this is something you may or may not have seen in Gen Chem. So I know a handful of us bring this up in Chem 124, but not everyone does. And what this spectrum is measuring is the amount of energy required to remove an electron from a given orbital. The y-axis here is the relative number of electrons. And so when we're looking here at carbon, what I can see is that there are three different signals in this spectrum. We're not going to be using photoelectron spectroscopy a whole lot, so I'm kind of going by it kind of quick. But I can see that there are three signals, and they are all of the same intensity. And that means that it's the same number of electrons in each one of those orbitals. And from this, we can actually gather some data about the energy for each orbital. And so we can use different units for this as it's presented in the photoelectron spectrum at the top. These are actually in megajoules per mole. It can be more convenient, and I tend to use electron volts when we are talking about the energy for a given orbital, right, or energy for a given orbital state. And this is largely just because the numbers are a little bit easier to use. But something we can note here is that this 1s orbital is way, way, way lower in energy than my 2p orbitals. And so this goes back to what we're used to thinking about, which is the valence electron configuration, right? That's some terminology that's been used ever since, Gen Chem, valence electron configuration. And the reason we tend to care about the valence electron configuration is because these are the highest energy or most accessible states, right? We can see that this 1s state is just a huge negative number, right? And what we're actually measuring down here, these are the binding energies. Right, and so this is the amount of energy that's released when an electron goes into one of these orbitals. But we can see here that the valence electrons are much more accessible, what we call core electrons. Just have such a hugely negative binding energy that they aren't going to react in the same ways as our valence electrons. So we tend to just focus on our valence electrons here. So what can we do with this, right? How can this allow us to update our electron configuration, right? We just have that straightforward, 1s2, 2s2, 2p2 configuration. So how can we actually put some numbers to this? And why do we need to put numbers to this? So let's look at that table that we have again of our binding energies, right? So these are binding energies. And so what we're going to do is we're actually going to try to make a more quantitative plot. So we're going to start here with a y-axis that is energy. And because these are binding energies, that's not what I wanted to do. Because these are binding energies, what I'm going to do is I'm going to look at this point as being 0, right? So this is the top axis here. This is a free electron and open, I'll put open orbital, right? That is my 0 energy state. And what happens then is that I have my, when these electrons get close enough to the atom, they can go into these orbitals, and it ends up releasing energy. So again, these are these negative values that we have. So I'm going to use electron volts here for my y-axis, just because I like them a little bit more. So if we have, minus 10, minus 20, minus 30 on my axis, so on and so forth, I can see that my 2s orbital is at about minus 19.43, right? So that would be about here. So this is where my 2s orbital falls. My 2p orbital, minus 10.66, right? So right here, and I have 3 of those 2p orbitals. And if I'm going to try to, plot out what's going on here with my 1s orbital, I'd actually have to break my axis, right? And say like way, 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 way down here, close to minus 300 is that 1s orbital. And so now I can go ahead and put my electrons in here, right? And this is a more quantitative way of describing the energy of these orbitals. And what I can see is that the energy, again, of that 2s and 2p orbital are much, much closer to 0 than that 1s orbital. So the much more interesting chemistry, the stuff that we're going to focus on, is in our valence orbitals, right? And so what we're going to see in inorganic chemistry is the valence orbitals isn't necessarily the highest quantum number. So it's not always just going to be the highest value of n, but our valence orbitals are going to be the orbitals that are high in energy and are close together. So what I've done here is I've drawn out my 2s and 2p orbitals in a specific configuration. And I said earlier that we are following Hund's rule here, right? Hund's rule. And again, this is something you've seen a number of times. Essentially, what Hund's rule is saying is that electrons are going to go in empty orbitals. I'm going to put the word degenerate orbitals in here. Degenerate just meaning of the same energy. So in this case, I have 3 2p orbitals that are degenerate in the same energy. And they're going to have the same spin when we put them in. So right, in this case, they're both drawn as spin up, and I have 1 electron in each of my 2p orbitals. So what is this, or what are we going to do with this, right? What have I been building to so far when we're thinking about electron configuration? Because this is carbon, it's something we've seen a lot, but for inorganic chemistry, what we want to do is we want to distill this down to some fundamental principles. And the principles we're going to focus on is, why does Hund's rule exist? What is it telling us, and how can we quantify Hund's rule a little bit more? So what I'm going to do for this is I'm just going to focus on the 2p orbitals, or the electrons in those 2p orbitals for digging into Hund's rule. Because again, we're going to extrapolate this and apply it to more complex systems in a little bit. So let's look at our 2p orbital state. So our initial state, right, the basic one that we're going to follow for Hund's rule says that we put 1 electron in each. But what I want to compare this to, and so I'm going to call this state 1. I'm going to compare this to 2 other hypothetical states, state 2 and state 3. And what we're going to do is we're going to essentially come up with some tools to analyze and think about Hund's rule and the way that it applies to these orbital systems. So for state 2, what I'm going to do is I'm going to violate the second part of Hund's rule, right? Meaning that state 2 is still going to have one electron in these two different p orbitals, but their spins are not going to be aligned. And for state 3, I'm going to violate the first part of Hund's rule, which says it says that electrons should go in different orbitals. So what if I paired them up and put them in the same orbital? Now, this means that their spins have to be opposite. According to the Pauli exclusion principle, we can't have two electrons that have the same set of quantum numbers. And so here, the spins have to be paired up to fit into this orbital. So these are my three different states. And what I want to do is I want to describe the energy of each state, right? So the energy of each state. This is really my goal. And so what I am thinking about here, so I'm going to see if I can move this down. All right, this is the goal that I have. And so when I'm looking at this, each of these states, right, each of them initially have two electrons in these 2p orbitals, right? And so we're going to call this energy 2p. And there's two of them for each. And so this energy is just the energy, right, of putting an electron into an orbital, right? So this is just putting the electrons into the orbitals, right? So each one of these states has this energy component. Because each one of them has two electrons that are in these 2p orbitals. And we can go back and we could try to quantify this using the previous slide. Right now, we're just thinking about a qualitative expression for these spin states, right? So this is our learning objective number 3 over here, is deriving expression for the energy of a given electronic state. So now what I need to do is I need to describe what else is going on in these systems, right? So if I look over here at state number 3, I have paired electrons. These paired electrons are in the same orbital, and so there's some amount of a Coulombic repulsion. Right, and this Coulombic repulsion is destabilizing. Now we're going to give this the term C, right? You might also see this written as pi with a little subscript C, just to represent a Coulombic repulsion force. And so this is destabilizing, right? Destabilizing means it is bad, right? So this means that the energy is above 0 for a Coulombic repulsion. And I can see in this state that I have one of these Coulombic repulsions. So I'm going to say this is plus C. So this is what is essentially going on in state 3, right? When we violate that first part of Hund's rule, we're actually introducing a Coulombic repulsion into our state. Now, the second part of Hund's rule, right, that the spin should be aligned, is a little bit harder to see. So let's imagine for state 1 and state 2 that our electrons switch places. Right, so I'm going to put it here and here. So let's say we're just going to imagine our electrons switch places. Right, and they switch places within each state. So that means that for state 1 in our 2p orbitals, it's going to look exactly the same. And for state 2, hopefully this makes it a little bit clearer what we're doing here. Our left-hand p orbital would have a spin down, and our right-hand p orbital would have a spin up. So this is what I mean by electrons switching places. Now, like I said, state 1, it doesn't look like anything happened, all right? And that is a very good thing. Well, I shouldn't say very good thing. It is a good thing, all right? So that means it's a stabilizing factor. So this is actually called a quantum mechanical exchange, right? Or quantum exchange, meaning these two electrons are indistinguishable from each other. And so this gets the term pi with a little lowercase e, or just a capital K. And I'm going to go with capital K because it's just easier for me to remember, and that's easier to use. So that means that we have one of these quantum chemical exchanges that can happen for state number one, right? So these are the energy descriptions for each state. So we have 2e plus k represents state number one, 2e represents state number two, and 2e plus c represents state number three. And so we want to keep in mind, right, Coulombic repulsions are destabilizing, quantum exchanges are stabilizing, right? Meaning they're a good thing. That means that the energy for K is actually less than zero, right? It's a stabilizing factor, right? So this has gotten a little bit messy, but we'll practice with this a little bit more. And so now what I can do is I can actually rate and think about these three different states and their relative energies, right? So now, again, I'm just going to make a plot that is relative energy, right? So I'll put relative energy. And so what we have is we have our state one is our lowest energy, right? And this was our lowest energy because it was 2e of our 2p orbitals plus k, and k is stabilizing. Our state two is in the middle, right? This is just the energy of these electrons being in these orbitals, right? As we derived on that previous slide, this is where I have the spins opposite. And my highest energy state is state three. And this is where I had the energy of those electrons in the 2p orbitals plus that Coulombic repulsion. And so this is really just explaining or giving us some extra terms to explain Hund's rule, right? So we want to be able to define, right, what is that quantum mechanical exchange, K, right? Where are we getting these Coulombic repulsions, C? And we really want to remember that K is good and C is bad, right? K is stabilizing and C is destabilizing. And so this is just the three different possible electron configurations for the 2p electrons in carbon. All right, so what is the goal, right? What should we have taken away from this? So we want to be able to describe the energy of a spin state using the orbital energies, Coulombic repulsions, and quantum exchange energies, right? We want to remember that these Coulombic repulsions are destabilizing, meaning they cause an increase in the energy of our system, and that quantum exchange is a stabilizing factor, meaning it lowers the energy of our system. And this allows us to create expressions for Hund's rule. And this is going to be extremely important for inorganic chemistry because we are going to have to evaluate different spin states for transition metal complexes. And it is not always going to be so simple as following Hund's rule, right? Hund's rule works well for basic electron configurations. It works well for organic systems, but as you go down in the periodic table, Hund's rule doesn't work so well anymore. We need to understand where Hund's rule comes from in order to apply it to transition metal systems. So where does this leave us? We're going to look at chromium next, right? I said we're going into a transition metal. And so what I want you to do before you go on to the next video where we're going to talk about chromium is I want you to try to draw out a general orbital diagram for the high and low spin states of chromium. In our very first class, right, this is one of the final question on LabPal said, you might write out the electron configuration of chromium to be, whatever it was, I think 4s2, 3d4. But based on the photoelectron spectroscopy of chromium, we actually know that it's different, right? We know that it is 4s1, 3d5. So what I want you to do is draw out an orbital diagram of the 4s, so I can write that on here so we remember it, of just the 4s and 3d electrons, right, for chromium. Go through and use these terms that we had for the quantum exchange and Coulombic repulsion to try to describe the energy of this high and low spin state, right? The one that has the greatest amount of nuclear spin and the one that has, or not nuclear spin, electron spin, and the one that has a minimum amount of the electron spin. And this last point is going to be really challenging, right? And this is what we're going to talk about in the video. But under what conditions would the high spin state be lower in energy, right? This one's going to be tricky. It's setting up an inequality, and we're going to talk about how that works in a little bit and kind of extrapolate this to inorganic systems. But for right now, right, we know these Coulombic repulsions, we got quantum exchange. We can start to describe expressions for Hund's rule. All right, so once you've gone through this, go ahead and boot up the next video, and you can see how far you got with the Chromium example and continue to take notes.